All right, ladies and gentlemen, part one of my video series on evolution. And for this one, I'm just going back to lesson one, looking at this whole idea of geologic time and how do we understand it. So, what is this whole idea of a geologic time scale? This is how scientists look back and basically understand the history of life on Earth and other major geologic events by basically studying the layers of different rocks and understanding how old and when different living organisms existed. So, to do this, we look at fossils. All right, what's a fossil? You generally think of this like it's dinosaur bones, but it goes much, much broader than that. It's any time that we basically have any traces or remains of a living thing. This can be anything from a footprint to a pile of fossilized dinosaur poo, all the way up to an actual frozen mammoth in the ice. So we'll look at those examples in a minute. Generally speaking, though, it's going to be most often the hard parts of an organism because for a fossil to be preserved, it can't just completely decompose, break down, and have every trace of itself eradicated. It needs to be able to last. So our most common types of fossils, these are going to be the casts and molds. A mold is that hollow space left behind when the original hard parts of the organism have dissolved away, but only after the hardened sediment around it turns into a rock. So if this were a chunk of sandstone, for example, then the seashell sitting inside is now gone. It's dissolved away, but the sandstone itself continues to have the shape of that seashell. And just like a jello mold, that mold can then fill in with minerals. And when those minerals seep in through these little cracks, they can then create a new rock inside of this hollow space that takes the shape of the original seashell. So you find a fossilized seashell, you may not actually be looking at the shell, any part of the shell, it could all be completely gone. And instead what you see is a cast of that seashell. This is actually what most dinosaur bones in museums are. So unfortunately, it means when you go to look at a dinosaur skeleton, most of the time what you're actually seeing is a rock that is shaped like the dinosaur bones and not actually a dinosaur bone itself, even though for all intents and purposes, you're looking at the shape of the body of a dinosaur. Okay, petrification slash mineralization. So mineralization means anytime that little minerals seep into the actual body cavity or space of the organism. So this stump over here, this tree stump, has actually been sitting in mineral water for millions of years until those minerals seeped into all of the little plant cells and then left behind those minerals to harden it into rock. So petra literally means stone. When you're petrified, either with fear or anything, we kind of mean you've been turned to stone. So petrification, mineralization, they're kind of the same thing. And it literally means you've taken something that wasn't stone before and turned it into stone. So while this may look like a normal tree stump, it's basically a rock. Carbonization, or the formation of a carbon film, that's this image over here. So while those may look like normal leaves, that's actually old leaves that have then been pressed between layers of mud and turned into a carbon film. So that's basically like a black soot mark, if you will. And it's just a very delicate layer of carbon to show an organism that normally may not be very well preserved. Leaves not really being very hard or solid parts like a bone would normally not be preserved, so these are very rare. Trace fossils, as I mentioned before, not all fossils are actually the living thing's dead body itself, but rather might just be evidence of how it had lived. So if you find a dinosaur's nest and all you have are the eggshells of where the dinosaurs had hatched, or footprints, or a pile of dung, you can learn about that organism even if you don't have a piece of the organism itself. So a trace fossil is just a special kind of fossil that tells you about the life of the organism without being part of the organism itself. Preserved remains. These are the best, most interesting ones because basically now you have not just a cast or a mold, you actually have the DNA, the original tissue, the material itself. So those Jurassic Park movies where they're always drilling into this amber and getting the DNA or the blood directly from a mosquito so that they have that genetic information about how to make their own dinosaur. That's where this idea comes from. And yes, it's real, but we don't have enough of it to necessarily unextinct dinosaurs. However, If you want, check out some of these links for the dinosaur tail feathers or the baby woolly mammoth. These are extremely well preserved. They have the skin and the hair and the muscle and the bone and the teeth. And so they can really get an enormous amount of information about a woolly mammoth, since they've got one that's 50,000 years ago old and frozen in ice. And basically, when we put together all that information, it tells us about how the organism behaved and what environment it used to live in. So changes in the environment over time and the adaptations that those organisms developed to meet that new environment are what we use these fossils for. So how do we know how old these are? Well, there's two major methods. One is relative dating, the other is absolute dating. I like to joke that this is not like taking it out for a nice dinner. This is finding out how old it is. Relative dating means it's comparison. So you don't need to know this phrase, principle of superposition, but the idea is if you are throwing everything into a pile, if you've got a pile of laundry in your hamper, then the oldest stuff ends up at the bottom of the pile. And as you add more layers on top, the newer stuff gets progressively closer to that top layer. So relative aging is comparing how relatively old the stuff on top is compared to how relatively old the stuff on bottom is. Absolute dating, however, is done through radiometric dating. In other words, this is radioactive materials that are breaking down over time. So when we talk about, say, uranium slowly being unstable and spitting out radiation and particles, as it decays, as it breaks down, we can actually measure the length of time that it takes for that particle to break down. And so we can actually measure its half-lives. And as uranium breaks down, as carbon breaks down, as certain isotopes of unstable materials decay, we can measure the amount of decay it has and say it's this old. It's very similar to in a crime drama show when some medical examiner looks at a dead body and says, this dead body is 3 days old based on its decomposition. Well, a paleontologist could pull a rock out of the ground or a fossil, look at the radiometric decay of that material, the radioactive isotopes, and say, this fossil has been decaying radioactively for the last 100 million years. All right. Next time, we're going to be getting into this guy, Charles Darwin. I hope to see you there.